Welcome everyone to this next part of the talk, which we are going to talk about using multi-stream inputs for fuzzing firmware. This is a joint work by CISPA and then Ruhr University Bochum over in Germany. And let's get into it. So let's catch everyone up on what we're talking about here in the first place. So the kind of mission of this type of or line of research, which there is multiple works in, is that we want to take in a firmware image, then we want to do some magic in the middle, some techniques, and then get some bugs out of it. And one of the main concerns that we have is that we do not want to actually use any hardware in the loop. And we are focusing on firmware here, which is non-Linux, so everything that we have heard from the driver generation for usual like Linux user space binaries, these don't apply here. So we have to do some work to actually make a firmware run first in an emulator and then do some fuzz testing on it, which is kind of my research direction, and see what we can get out of there. So this is somewhat what the current state of the research is already giving us. So what we already managed to do is that we can take in a firmware, then do some analyses and have an emulator basically auto-generated to run this. As we can see here on this picture, every firmware typically interfaces with different types of embedded devices. Its peripherals here. And in this case, we can see a temperature sensor and a serial interface, and then also a timer. And the way that we are dealing with the input of these is that we take in the input from a fuzzer. In this case, oftentimes it's AFL. And what AFL will do, it will see a binary input, and it will mutate this binary input, and then it will translate in the emulation process. We will translate these binary inputs one by one into responses from the peripheral. And if we look at this behind the scenes, what is actually going on is that each of these bytes might be interpreted in a different context. So the very first byte might be interpreted as a temperature, and then the other ones might be one like a serial interface input, and so on. And this is something that the fuzzer doesn't have any view into. So all the fuzzer sees is that we have a binary input, which is then one at a time interpreted. And this will lead to some issues along the line, down the line. So let's try to understand what's going on there a bit more. So very first, we have these three peripherals from before, and now we are going to look at some of the code of the Marlin firmware, which is a 3D printer. And 3D printer's job, of course, is to print some 3D objects in the end. And so what the Marlin firmware is doing is that in its main loop, so this is running when nothing else from the outside comes in, you kind of get the temperature in and then do some 3D printing job advancements. Then the second one, what we get asynchronously as well, is interrupts. So interrupts are a way for peripherals to give some notifications into the process asynchronously. So whenever an interrupt comes in from the serial peripheral, for example, the main loop will stop executing, and then we get into this interrupt handler. One of the important things here is that will be important down the line is in this interrupt handler, what the logic is doing, it's reading the status of the serial interface and then sees whether there is any data available to be read. And if there is any data available to be read, the next byte of input is taken and pushed into the so-called G-code queue, and this G-code queue is the queue that holds the G-code, which tells us how to do the 3D printing. And then we have a timer as well, so we want to check every now and then that our print nozzle is not too far down. So we need to take some actions if we are about to collide with our object that we are printing. We can have a representation here that kind of shows how this firmware interacts with its input. And so what we can see is that we have different rows here, and every row is one of these different code components that we have seen. So the main loop, it's reading its input. The serial peripheral is also read via the interrupt handler, which is in red, and then we have the timer as well in blue. And what we can see in this case, for example, is that, first of all, the main loop is running, it's reading its temperature reading, and then an interrupt from the timer comes in, and we check the Z flag. And after checking the Z flag, we say, okay, we don't need to do anything because the nozzle is not about to collide. And then we get back to the main loop and so on. And this is kind of the high-level overview that we would logically see as this input is used and how the firmware takes in its input. And this is in very stark contrast to what the actual fuzzers are seeing prior to this work. So actually what the fuzzer is just seeing is a bunch of bytes. And we see these colors here, which represent what each byte is going to be mapped to. But this is something that's not visible to the fuzzer. For the fuzzer, it's just a byte, another byte, and another byte. This leads us to a pretty big issue, which we call the avalanche effect. So different bit flips in early parts of the input by the fuzzer can lead to pretty serious consequences down the line and misinterpretation of the input, as we will see here. So the very first bit flip that we want to look at here is this data availability byte, which we have talked about. So whenever this bit is set, a new character is there, so the firmware logic will kind of consume its next input, which will be a serial input character for the G-code queue. And in this case, what we assume, there is a change that the fuzzer flips a bit, such that the read or the data availability flag is now 0. So what the logic will do, it will skip reading it, this serial character, and instead it will go back to the main loop and kind of consume this next character as a temperature. And we can see this here by a mismatch in colors. What was previously a red, so a serial interface byte, is now interpreted as a color, and this kind of goes on to this misalignment. And we can also see this here in the more exploded diagram as well. So anything that was previously a serial byte is now like the Z flag value, and it kind of spirals out of control from there in an avalanche effect. This is one of the more intuitive ways of how this can go wrong, and there is also something different where you can change the processing time. We said, okay, if there is a Z flag, we want to do some additional computation because we are about to collide, and this just takes more time. And in this case, what we can end up with is that because we take much more time, the next interrupt is already queued up, so we cannot even go back to the main loop, but we go to the next UART, and then we have this kind of chaos or avalanche effect as well. This leads us to the changes that we applied to this type of process in our work. And there are two kind of areas of changes that we applied. So the first one is extended feedback, which is basically making the fuzzer aware that it's testing firmware and gives it more information about the process. We won't go into the details here, and you can check this out from the paper if you like. The second one, which is the main contribution, is splitting up the input, not into one serial byte stream of inputs, but then into multiple streams so that the fuzzer knows, okay, I have different types of inputs, and if I mutate the input in one input stream, as we call them, we don't have any effects on the structure of the other input streams. And this is kind of intuitive and also easy to understand, and then you start actually implementing it, of course, and you get some challenges there. So what we do in the prototype is that we split this the input up into many streams, because it turns out you have many peripherals, and every peripheral has different MIO registers, and it kind of goes into hundreds and thousands of streams. But then if we think about this Marlin firmware, which is a 3D printer, we basically want to give it valid G-code. So we have one stream, which is responsible for most of the logic, and we have 1,000 streams to pick from. And we have different techniques to kind of, over time, figure out which of these streams are actually impactful for the execution, and then we have, over time, a higher bias towards the fuzzer picking the interesting streams. And we use Thompson sampling in that case. You can read about these details in the paper as well. Let's get to some results. So we are kind of following along these 3D printing example, And this is what we can see from a coverage perspective. So on the bottom, you can see the single stream fuzzers, even a version of our fuzzer that uses single streams. And what these streams have as an issue is that you cannot really keep a valid G-code input, because whenever you perform a bit flip, you will destroy your own G-code input, and this kind of leads to these issues where you cannot put together meaningful G-code commands and not series of G-code commands. And this is different for the multi-stream representation, so we're able to increase the code coverage there by 4 or 5x. Other examples, here we have a combination graph. What you can see here is over time, we plot the coverage, and then as well as there are different symbols, like a star or an explosion symbol, and these denote the timings at which the first time the specific bug of this target was detected, or there was a crash that corresponded to this issue. And what we can see here is that we have different examples where the multi-stream input is the only one who is able to really trigger these bugs. And the reason for this is that, at least in a 24-hour time frame, and then it kind of depends on the target. The reason for these is that in the first example, what we need to do is we need to create fragments of packets, and these fragments, when they get reassembled, there is an issue with offsets in the calculations, and then you have an out-of-bounds write, for example, and this requires the fuzzer to first create and then maintain the structure of multiple fragments, and this is very hard to achieve for these flat binary inputs as well. And then on the right side, we have a very elaborate type of initialization handshake of a Bluetooth layer. And in order to trigger this vulnerability, you have to first find and then maintain this handshake in order to then afterwards mutate this efficiently. And this is also where it's pretty hard for these flat inputs to work correctly. And with that, we have some results. Of course, you can check out our artifact on GitHub as well. It went through the artifact evaluation process, and can find all the details in the paper. And with that, thank you for your attention, and I'm open for questions.